Okay, now we will start talking about the dropping zone, which is very important zone in the blast furnace. This dictate all the aerodynamics of the blast furnace, and the figure shows the dropping zone, which you are already familiar by now. So, at the bottom you have pulverized tuer through which the oxygen or hot air is blasted, and the pulverized coal or oil or anything else is injected through this pipe, and the combustion occurs at the front of the tuer. So, hot gases goes up, and as you know, in the cohesive zone it is a mushy zone where liquid iron slag is in semi solid form and start melting in the lower boundary of that. So, liquid and slag drop down, gases are going up, and this cohesive zone give big resistance to the gases. So, very high pressure drop in this region. So, we would be talking, so in this region is mostly coke which is in the solid state, all other thing is in liquid or fluid state. So, slag and liquid iron is flowing down, gases, reducing gases are going up, and due to the combustion of the coke is getting consumed, and due to this consumption is descending down to replenish the consumed coke here. So, you solid is also moving down, liquid is moving down, slag is moving down, gases are going up, and in this region near the or in front of the tuer, you are having a gas movement in the perpendicular direction of the liquid and solid flow, and this boundary shows the dead man where coke is mostly in inactive form. So, and this gives more mechanical support, of course, the dead man. So, this is a very complex part in terms of aerodynamics of the blast furnace, because this part dictates how the gases are going to distribute in the upper part of the blast furnace, which is important for the reduction. So, main phenomena which occur here, liquid, metal and slag, and they are usually non-wetting in nature for with respect to coke, flown down through porous coke matrix. So, you are already now familiar by pegged bed. So, it is like a pegged bed. So, this is a coke matrix, gas flows across. So, near the raceway region or near the tuer, and counter current flow of liquid occurs in this region, and liquid shift holdup over raceway are observed. So, melting liquid is flowing through this. So, liquid holdup in this region one can expect. So, quite a lot liquid holdup is observed, and the bed of coke also slowly descends in this direction. So, this is some with respect to liquid is like a co-current flow, which I think you are familiar by now. So, we would be talking really in a more detailed way about this region in the next few slides, and seeing that how does this zone affect the performance of the blast furnace. So, the first one is about the flow of gas and liquid in Bose region. As you know, this region known as is a dropping zone or the Bose region we call it. So, we are talking about that, and we said about the liquid holdup. So, what is liquid holdup? I think before we move on to it, you should be familiar about this term. So, liquid holdup, as you know, in the packed bed or in any packing, when you are flowing the liquid from the top and injecting the gas from the bottom, at a very low liquid flow rate and gas flow rate, you will see the liquid is just dripping through this packing and coming out, which what we call is a normal operation. But if you increase the gas flow, you will find that some liquid is just now hanging in between the voids of the packing, and that condition usually we call as a loading. And if we suppose keep the liquid flow rate same and increase gas flow rate further, then one situation will come. So, gas velocity is high enough or gas drag is high enough, which does not let the liquid flow down, and that situation is usually known as flooding. And in that condition, gas is very difficult for gas to come out. So, gas comes out in the form of bubbles. This also shows in pictorial form. So, this is sort of a bit loading where most of the packing surrounded with a liquid film or like that, and in this one at some places it is there and at some places it is not. So, the liquid which is now you have to familiarize couple of terms in this scenario. One is static holdup. The static holdup, it is the amount of liquid that remains in the bed after liquid flow is stopped and bed is drained. So, this is the one if you stop the liquid flow here and let the bed drain. So, in between the particle some liquid will stay there, and that is the one which what we call the static holdup. And there is another holdup is called the dynamic holdup. It is the amount of liquid that drains out of the bed once liquid flow is stopped. So, this is what when you are stopping the liquid flow, still there would be some liquid which is flowing through the voids which will come out. So, when you stop the liquid flow and the liquid which is coming out from that moment till it drains out, that liquid you call it a dynamic holdup. So, static holdup between the particle is just staying over there after the liquid flow is stopped. Dynamic holdup is keep on, it is a moving liquid through the packed bed. So, once you stop the liquid flow, whatever you collect that is known as the dynamic holdup, and the total holdup is nothing, is the combination of both the addition of these two. So, addition of static and dynamic liquid holdup known as the total holdup, and usually it is presented or presented in the form of meter cube per meter cube, that is the liquid volume what one collects is divided by the packed bed volume is known as the liquid holdup. So, usually the it is a non-dimensional quantity, it does not have the unit in that form. So, it is a meter cube per meter cube basis in terms of fraction. So, this is these are the two very important terms which are used in the liquid flow through the packed bed. And in this case we have in fact a very complex situation. Not only the liquid is flowing down, gas is also flowing up, and when we start putting fines, pulverized coal or other thing, so those unburnt coal or ash, that also goes up. So, that is also contributing towards the blocking of the voids. So, it is a quite complex process, and we will be talking a little bit more on that. So, if we take a flow of gases and liquid through packed bed, this figure represent what happens. So, when gas is flowing upward, liquid is flowing downward, the situation is known as counter current system, which you are already aware of it from our last lectures. So, in this counter current situation, there is first thing, suppose there is no liquid flowing. So, only gas is flowing in and coming out, what we call the dry bed, and this is represented schematically by this line A. So, as the gas velocity increases, your pressure drop increases, more and more resistance is felt by the gas. So, pressure drop increases. So, this is the normal situation which we have already discussed, and this type of flow using the Argon equation we can calculate the pressure drop, which already you are familiar with. Now, when you start the liquid flow through this, what happened, because some liquid is depositing in between the particle and some liquid is flowing through these voids. So, essentially your void fraction has reduced, and one is the void fraction is reduced, and that gives more resistance to gas to pass through. So, obviously your pressure drop is increases, and which is this second curve is showing when it is wet and in fact no liquid is flowing, only packing is wet and the liquid is drained out, what we said about the static hold up condition, where amount of liquid that remains in the bed after liquid flow is stopped and bed is drained. In that condition, so this is the wet drained packing. So, liquid is not flowing, it has been drained. So, only static hold up is there, which is between the particle, and that is anyway reduced void fraction a bit, and due to which the pressure drop has increased. Now, instead of just a drained packing, liquid flow is there. So, when liquid flow is there, it will occupy this spaces between the particle through which it will flow down and come out. So, again it is occupying more voidage, more space in the packing, which will create more resistance for gas to flow through this. So, pressure drop will increase. So, now as the gas velocity increase, naturally in the starting there would be a uniform sort of pressure drop, resistance would be in fact the liquid would be facing more gas drag when gas velocity is increases and liquid flow is constant, and gas velocity is increases, then the drag force on the liquid will increase. So, then which means the resistance for gas flow will increase and pressure drop will increase. So, as the gas velocity increases, pressure drop keeps on increasing, but at one stage what is going to happen, the gas velocity is quite high enough that some of the liquid is getting entrapped. So, the drag force on the liquid at few places is high enough, which is entrapping the liquid between the voids, and so it is having a more resistant felt. So, it is trying to occupy the spaces which are empty. So, it builds liquid settle down in between the voids, and that is where more resistance is faced by the gas, and that phenomena, that part is represented in this curve by x and y. So, this phenomena is known as flood loading. So, in this one liquid is more loading in between the packing. So, that is a loading condition, and one situation will come, then most of the voids even filled up with the liquid, because the gas velocity is high enough. If you keep on increasing the gas velocity, all the voids have liquid has occupied all the voids, then gas has to travel through these liquid as bubble, and which that is the situation which we described in this figure schematically, where gas is coming out as a bubble through the liquid in the packed bed, and that is the flooding situation. And this is a very bad situation, and one cannot operate any reactor in this condition. So, and the pressure drop sharply increases. So, as you can see from the graph, if you increase the liquid flow rate, naturally the situation will become worse, and at high liquid flow rate your pressure drop becomes very high, and this situation deteriorate further. At a very then low velocity you will encounter with the flood loading situation and then the flooding. So, certainly blast furnace cannot operate above this, it is a abnormal operation. Problem will come, the liquid metal and slag would be carried out in the upper zone, which is lower temperature zone, and it will deposit over there and solidify. So, and blast furnace operation would it would be like a abnormal operation. So, blast furnace should be operate somewhere in this region for the maximum efficiency. So, for that purpose one has to have a proper knowledge about the liquid holdup, how much liquid holdup is there and what sort of gas velocity should be there. So, one can operate blast furnace efficiently in this range. So, we will be now talking about the liquid holdup. Before we go, so you know this is a high temperature region where we are talking about 1400 degrees Celsius temperature. So, it is very difficult to visualize that in live way. Some attempts have been made to see through cameras and have been successful, which are the recent one, but people have tried to visualize this phenomena using various other visual technique, dye and other, and one of that, the recent one using the X-rays and trying to replicate the blast furnace dropping zone phenomena and see how the liquid and gas behave. So, this is one picture of that, where the liquid flow is coming from the top mimicking the iron and slag, and gas flow is coming from the tube from the side as in the blast furnace, and raceway is formed, and one can see how this liquid shift is occurring. So, it is going away quite, and one can see also quite a lot liquid hold up. In this one, one has used sort of a, water. So, the density difference quite a lot. So, one would be seeing a high deviation, big deviation of liquid away from the raceway, but in actual situation density is almost 7 times more. One would not expect that much deviation here. Can expect some deviation, but not that much, and certainly liquid would be going more at the back and coming down this way in the raceway region. Probably we will see in one of the video later on about this phenomena in the raceway, but about the liquid flow, this cold region one, this next slide will show you a video about it, which probably you can see in this. So, this video shows about that picture which we saw just now, that how the liquid flow occurring in the dropping zone. So, you can see that this is a dry layer bed in the starting, and then liquid from the top is poured through the tubes, and you can see the liquid which is sort of a lots of liquid holdup you can see here, quite a lot liquid holdup is there. Gas has not started yet, and once gas starts you will see the liquid will start moving, but at the moment now gas has started you can see, and liquid is pushed away, here. So, that is due to the high drag by the gas, and now the raceway, and see how the liquid has gone up really from the side and on the other side. So, very high drag, once the raceway is formed, very high drag on the liquid, and it is shifted. It is not only shifted, you can see also the liquid hold up. Some of the liquid is just not coming down, as you will see plenty of liquid hold up, which is restricting the flow of the liquid near the raceway, and this will absorb most of the affect the chemical reaction and heat transfer in this region. So, look at all the hold up at various places. Now, this shows when the liquid has been stopped, but so you can see the static hold up in one few regions places you can see quite a lot hold up is there, and there is no liquid is coming out, that is called the static hold up. So, this would be like your liquid ion. So, this is one of the thing, and now so I hope you understand now with that what is the importance of the liquid hold up.